A common situation when you're applying math ideas is to decide on some set of conditions that you're interested in and trying to figure out what sets of values would satisfy those conditions. And you can represent that set of values as a curve that you've graphed. So let's do a simple situation here. Let's say that I've got a line. This isn't an asymptote, even though I'm drawing it as a dotted line. This is just a line. So let's say I've got a line at like y equals -2, and then let's say I've got a point over here at, let's say 3, 2. Okay, so here's the condition I'm interested in. I'm interested in the condition. The set of points that are all the same distance from P as they are to the line. So let's start getting a sense for what this might look like. Think about, there's like exactly one point that you're sure is the same distance from P and to the line. Like the distance from our mystery point to P is the same distance as the distance from the mystery point to the line. So think where that might be. Pause the video if you want. Hopefully you said right here. So the point at 3, 0 has a distance of 2 from P because it's just straight up by 2. And then it's also got a distance of 2 from the line because it's straight down by 2. But if you imagine going over a little bit, I'm still a distance of 2 from the line because you can just always go straight down by 2. But I think I'd have to go up a little bit in order to have a distance of 2 from P. So like this straight line distance should be 2. And this distance down should be 2. And so then if you imagine connecting them, it looks like I'm kind of getting a curve there. And then because the situation is symmetric, presumably it would be the same on the other side. So you can sort of think about what shape this looks like. And just because it looks like a shape doesn't mean it really is that shape. But let's try and see if we could come up with an equation that describes this set of points. So we're interested in all points x, y that satisfy this equation. So let's go ahead and label an arbitrary point xy. That's this one. And so what I want to know is what's the relationship between x and y so that it's always true that this distance is the same as that distance. So let's give some more labels. Let's call this distance 1 and let's call this distance 2. Okay, so what do we know? Could we write an equation for distance 1? Could we write an equation for distance 2? I hope the answer is yes. Well, distance 2 doesn't really need much of an equation. It's always 2. I guess it's not always 2. Excuse me. So it's 2 down from the x-axis to the line. So let's describe this vertical distance in 2 parts. Here's distance 2. So this part is always distance 2. This part, how long is that part? I hope that you said y. So you can think about this total height as being 2 plus another y. So distance 2 is always just 2 plus the y value of my point. What about distance 1? So distance 1 seems like we need the distance formula. So it's going to be like the difference in x's squared plus the difference in y's squared, take the square root. So the difference in x's squared, let's see, this x coordinate is just x. This x coordinate is 3. So that's distance in x's squared. Distance in y's squared is y minus 2 squared. Cool, so we've got equations for d1 and d2. And remember, I was interested in all points that are where d1 is the same as d2. So let's set those two things equal to each other. Let's say that 2, whoops. Let's say that 2 plus y equals this giant square root. X minus 3 squared plus y minus 2 squared. Okay, so we're just about to restructure this equation so that it looks more familiar. Like I think looking at this, you might not know what shape this is. But I want you to focus on the strategy so far. I gave you an English language description of something that I wanted to be true. The way that you go from there to an equation of all the points that satisfy this description is first you draw a little sketch. Then you add a point that represents an arbitrary xy value that satisfies the condition. And then you try and figure out how can you express this condition using variables? So the condition was the two distances have to be the same. So I introduced variables for the two distances. And then I asked, could I write equations for those two variables? And the answer was yes. And then because the two distances are the same, I made them equal to each other. So when you see this kind of problem again, I'm going to give you a new condition here, and it's going to be up to you to draw a little sketch, make the point, like introduce variables, figure out how to describe them with equations, like set the equations in relation to each other and so on. All right, let's finish this up by, so you could like plug this into Desmos right now and it would show you what the curve looks like. But like this curve might look more familiar if we put the equation in a more familiar form. So let's go ahead and restructure by squaring both sides to get rid of the square roots. So now we've got 2 plus y squared equals x minus 3 squared plus y minus 2 squared. So you might be thinking, it's sort of like vaguely connected to a circle because like we've got an x squared term and we've got a y squared term, but actually it looks like we've got two different y squared terms. So let's keep simplifying and see where it takes us. I'm going to expand everything here. So if I multiply this out, I'll get 4 plus 4y plus y squared. If I expand this, I'll get x squared minus 6x plus 9. If I expand this part out, I'll get y squared minus 4y plus 4. Okay, so here are some things I'm noticing. Let's look at what cancels. So here's the equal sign. I've got a y squared on the left and the right. So if I subtract y squared, now they both go away. I've also got a 4 on the left and the right, so I could subtract 4 on both sides, and those go away. So now I've got 4y equals all this stuff with x minus another 4y. All right, well, so if I want to set it in a y equals form, maybe I should add 4y to both sides. So that would make this now 8y. And you know what? Now I regret expanding this. It seemed like a good idea because maybe it was going to help me see some stuff that canceled. But now I feel like maybe I want to recombine them. So let's pretend we'd never expanded it at all. Because this seems like a cleaner form than keeping the quadratic expanded. And they're both equivalent. They're both the same thing. Oh, great. So now we've got, let's divide through by 8. So now I've got 1/8 x minus 3 squared. Ta-da! So you should now know what shape this is. This is an upward-facing parabola with a scale factor of 1/8. Which sort of matches my picture up here. It seems like it should be something like this. It's been right shifted by 3, which sort of makes sense. You notice that the vertex here lines up with this point here. Like these are all sort of in a line. Cool. Try to do the whole process again yourself. So I'm interested in all of the points that lie the same distance from a point P at -5, 1 and a line at y equals 5. So go ahead, draw in the point, draw on the line, draw a little sketch, or like fill in where you think the points probably are. So like make a guess, where do you think the curve probably is? Label one of the points x, y, and then go ahead and derive the equations and get all the way to the end until you get to a form where you know what it looks like. Okay, pause the video. All right, and now I will solve the problem for you. So let's see, -5, let's call this -5, 1 is the point right here. Let's call that P. The line y equals 5, so 1, 2, 3, 4, 5 is like about up here. Okay, so if I want all the points that lie in equal distance between those, just the same way I did last time, it seems like if I do a point that's halfway between the line and P, that's going to work. So since this is at 1 and this is at 5, this must be at 3, because that's a distance of 2 up here and 2 there. And then it seems as if I move this direction, I'm still going to be a distance of 2, but I'm going to be a longer distance here. So it seems like I got to move it down a little bit so that that's the same distance as that, and it's going to be symmetric. So my guess is it's going to be a curve that looks something like this. And that's just based on my kind of intuitive geometric feelings, my geometric reasoning. So let's go ahead now and add some labels and derive the equation ourselves. So if that's xy, I'm going to call this distance 1, and the straight line distance up here, distance 2. You might be wondering, like, I could get a lot of distances to the line, right? I could draw a line from here to there, or a line from here to there. But this is the shortest distance. Just drawing straight up is the shortest of all the distances. So I want d1 to equal d2. Okay, let's get some equations going. So d1 is this sort of diagonal distance, so that's going to be the distance formula. So it's going to be the difference in, if I imagine this is like a right triangle, it's going to be the difference between the two x coordinates. So x minus 5 squared. And then I've got y minus 1 squared. And then distance 2 is this sort of vertical distance. So I could imagine it this way. So the line here is a distance of 5. So from here to there is 5. But then I want to subtract the distance from here to my point. Because if I have, let's do this in another color. Because if I've got this total distance here is 5, but then I subtract this distance, which is y, this is 5, that means the distance left over, which is the distance from the point to the line, must be the total distance minus that distance, or 5 minus y. All right, so let's do that. 5 minus y. All right, and I want those two things to be equal, so let's set them equal to each other. 5 minus y equals the square root of this stuff. I'm going to go ahead and square both sides. So here, the square root is going to get undone, and here it's squared. Okay, so this is feeling familiar from last time. This time I'm not going to expand the x term, because I eventually want to get to y equals something. So I'm only going to expand the y terms in the hopes that something will cancel here. So on the left-hand side, I've got 25 minus 10y plus y squared. Here's my x term, which I'm not going to write. Here I've got y squared minus 2y plus 1. Okay, so this is looking good. So I've got a y squared on both sides, so I can subtract those. And it seems like that's the only really obvious thing that's canceling. So let's do this. Let's put all the y's on one side and all the constants on the other side. So I'll add 2y here, so that gives me negative 8y. I'll subtract 25, so that gives me negative 24. And then the x term still looks like this. And now I can divide through by 8. Well, I guess I'll divide through by negative 8. So that gives me y equals negative 1/8 x plus 5 squared. And then, so remember, I'm dividing this by 8, and I'm also dividing that by 8. So that's going to give me positive 3. Okay, and now let's make sure that this equation fits with the picture up here that we think it should be. So I'm noticing that the leading coefficient is negative, which means that I've got a downward facing parabola, so that seems to fit. Here I've got a vertical shift of 3, and sure enough, I think that my vertex here was supposed to be at 3, because that was halfway between 1 and 5. Here it looks like I've left shifted by 5, which also seems to fit where the vertex is. Cool. So if you did it, good job. What we're going to do from here is start trying to generalize. So you might have noticed a pattern between the last two examples. The vertex always seems to be in the same place relative to this line and this point. So think about that. Also think about what's going to affect why was the first one an upward facing parabola and this is a downwards facing parabola? Like what about the original setup led to that result? It would also be curious to think about why the 1/8. In the other example, I forget what it was. Was it 1/10? I don't know. Anyway, it was some scale factor. So like, is there something about the original setup that determines the scale factor? Like, what's that relationship? So once you understand how the original point and line can be used to predict all of the features of the resulting parabola, now you've really like done some math. All right, so that's where we're headed in class. Good luck.